In this lesson, we are going to be talking about strong versus weak acids and bases and what happens when you react an acid and a base together. So first, let's talk about strong acids. In the Bronsted-Lowry model, a strong acid is a forceful proton donor. H plus is also known as a proton. It has to give away its proton, its H plus. And once the strong acid donates that, it never comes back. And that has to do with potential energy. The potential energy of the acid, like HCl, which is one of our strong acids, is much higher than when the donation happens, when it becomes H plus. So energetics dictates that this will happen in a singular direction. There are only 3 strong acids that you will ever see in this class, and that is hydrochloric acid, sulfuric acid, and nitric acid. There are others, however. There are 7 in total. The other ones being HBr, hydrobromic acid, hydroiodic acid, HI, perchloric acid, HClO4, and chloric acid, HClO3. But we're never going to use these. We'll only ever use these. We can compare our strong acids to weak acids, in which they are a wishy-washy proton donor, H+. It can give away the H+, but it may regain the H+ after some time. Unlike the strong acid, once it gives its proton, it never comes back. In a weak acid, it can come back, it can donate it again, it can come back and forth, back and forth. And that is because the potential energy difference between the products and the reactants, like let's look at formic acid, HCOOH. This is the acidic form, and the form in which it's donated looks like this. There is a relatively similar potential energy between the two of them, so neither is more favorable energetic-wise. So every acid that is not a strong acid is a weak acid. And if it's not one of those 7, it is a weak acid. This includes anything that has a carboxylic acid, the COOH group, that's a carboxylic acid. So like formic acid, acetic acid, which is vinegar, CH3COOH, benzoic acid, C6H5COOH, so anything with that COOH group, going to be a weak acid. And then other ones like phosphoric acid, H3PO4, that's weak, and many others. There are thousands of weak acids. Most acids are weak acids. Now on to strong versus weak bases. A strong base, much like a strong acid, just in reverse, is a forceful proton grabber. If an acidic hydrogen is anywhere to be found near the strong base, it will take it. It's like a shark eating anything in its path. There is only one strong base that we will look at in this class, and that is hydroxide, OH-. Again, the energetics dictates that this is a strong base. When it has a proton attached, it becomes water, and this, as you know, is very low in potential energy, and thus more stable than the base form. Last but not least, a weak base. A weak base is a wishy-washy proton acceptor, much like a weak acid. It can take a proton, an H+, but it may give it back after a few seconds. Every base that is not hydroxide is a weak base. There are thousands of examples. Anything that has a nitrogen group, like ammonia, NH3, that's a weak base. Methylamine, CH3NH2, that's a weak base, and many others. Now we're going to look at acid-base reactions. In order to have a reaction between an acid and a base, both an acid and a base must be required in the reactants. The reaction itself is a proton transfer, an H+ transfer reaction, where the proton from the acid gets transferred to the base, much like tossing a football from the quarterback to the receiver. Many acid-base reactions are reversible, so the proton, the H+, the football, may be passed back and forth. We're going to classify each of the reactions by looking at what the products are and the reactants are. Let's start with the first one. HCl, we know, is a strong acid, so I'm going to label it as such, strong acid. And this one's ammonia. It is not hydroxide, so that makes it a weak base. So this is a strong acid, weak base reaction. The products are Cl- and ammonium ion, NH4+. here. And these can actually be labeled. They have specific names. When an acid-base reaction happens, it produces an acid and base as the products because the proton is moving. Those are known as conjugate acids and conjugate base. Much like in a language when you conjugate a verb, the base of it is the same, just the ending changes. Here, the conjugate acid and conjugate base come from the acid and base that you started from. So let's do NH4. This is the conjugate acid. That's because it has a proton that it can get rid of it, making it an acid. But because it is the result of the weak base, it is the conjugate acid. Now, chlorine minus, you might be tempted to label this as the conjugate base, but in reality, this is not a base. Not a base. That's because once this proton has been dissociated from the chlorine, it will never take it back. That's what makes it a strong acid. So if it will never take a proton back, then it's not a base. It has to be able to accept a proton to be labeled as a base. That doesn't get a label. All right, let's do the second one. Hydrofluoric acid, we know from our list, is not a strong acid, thus it is a weak acid. And this is formate ion, and we know that this is a weak base because it is not hydroxide. And on the resultant side, we have F minus. This is the conjugate base. Because this is a weak acid and it can take its proton back, that makes this a base, and that makes this the conjugate acid. Here's the proton it can donate. So this is a weak acid, weak base reaction. Here we have formic acid, a weak acid, and hydroxide. We know that this is a shark. It is a strong base, meaning it will forcefully take the proton from the weak acid and never give it back. That would make the resultant base the conjugate base because there's a place for the proton. However, this is not an acid. This is nothing. This is water, not an acid, because it will take a hydrogen and never give it back. And again, this is due to energetics. The potential energy of water is much lower than the potential energy of hydroxide, whereas the potential energy of our formic acid versus our formate ion are relatively the same. That's what makes it weak. So this is a weak acid, strong base reaction. And lastly, we have nitric acid. This is a strong acid, it's on the list, and hydroxide is a strong base, and the resultant are not conjugate acids or bases because they will never take their proton back. Once they donate, once they take it, never goes back. All right, those are acid-base reactions.